Welcome, ladies and gentlemen, to our lecture on force problems and friction. So let's start out by looking at an example problem that should be instructive. Jim Bob doesn't have a great parking brake on his 2100 kilogram car, and he parked it on a hill in neutral. The parking Bob released while Jim Bob was in the store, so the car is now rolling freely down the hill. If the hill makes an angle of 30 degrees with the horizontal, what acceleration will the car have down the hill? So let's start this problem the same way we always do. Let's draw a picture. We have a hill here, and we have a car on it. And we know what this angle is, theta. They told us theta is 30 degrees. And we know what the mass of the car is. It's 2100 kilograms. And we know that little g is 9.8 meters per second squared. So now we want to know what acceleration the car is going to have as it rolls down the hill. So when we're looking at a car and it's freely rolling down a hill, there's a small enough friction force acting on the car as a whole that we can neglect it, okay? And we aren't really concerned about the wheels turning because they make up such a small fraction of the car, okay? So in its simplest form, I drew this picture of the car, but I could maybe draw it instead like this. I'll just draw the car as a brick, okay? A car with nobody driving, just kind of frictionlessly sliding down a hill, if we consider that to be the way it's working when it's just freely rolling like this. It's really just a brick sliding down a hill, okay? So I draw it this way, and then the next step that I want to do in a problem like this is draw my forces on it, okay? So we know we'll have the force of gravity pulling down, and we know we'll have the normal force pushing perpendicular to the ground, okay? And in this case on this problem, those are all the forces on the car, okay? And what we're back to is just that same block on a ramp problem that we had before. Okay? So with this problem drawn in this simple way, we're back to just our block on a frictionless ramp. Okay? And we'll solve it in the same way we did before. We'll choose a coordinate system where x goes along the ground and y is normal to the ground. And then we'll solve in the x direction. Remember that gravity, if we break it down into its components in our new coordinate system, has FGY pointing in the y direction and FGX pointing in the x direction. So in the x direction, we have FGX. That's the only force that's in the x direction, okay? And then that's equal to MA in the x direction, okay? Which is equal to ma, because all of our acceleration is in the x direction. And then if we want to solve for a, it actually turns out that we already know everything in this equation. There's nothing more to solve. We have fgx on top and m on the bottom when we solve for a. And then if we use our trig, we know that this fgx is mg sine theta, okay, this angle is also theta, over m equals g sine theta. So A equals g sine theta. And in this case, they gave us the mass of the car, but it turns out it doesn't even actually matter, right? We talked about this last time. When something's sliding down a hill in this frictionless fashion, it turns out that the mass of the object isn't important. We just have this acceleration that's g times sine theta. So it really just depends on the steepness of the hill. And in the situation where we make the hill, if we just keep increasing theta, we make the hill steeper and steeper. When we get to theta equals 90 degrees, the hill is straight down, then we're back to free fall, right? Sine of 90 degrees is 1. And this general expression can be specified to the instance of free fall if we just keep making the hill steeper and steeper until it's straight down. Then we're back to free fall. We're just falling again. There's nothing in the way anymore. Okay? So that's a pretty simple problem. It's just a block on a ramp with no friction. But what about when we do have friction? Okay? So what about friction? We've probably all set something big on a hill before, okay? And it doesn't just go sliding off down the hill. So why is that? Well, that's because there's friction between the box and the surface of the hill, okay? So how does this problem change if we look into friction? To consider that, we're first going to have to look into friction a little bit. We need to understand friction a little bit better. So friction is a force that's applied when two surfaces are touching each other, okay? Objects in the real world have a kind of stickiness to them. And when two objects are touching each other, there's this kind of stickiness between the two. And this is due to, it can be due to the shape of the object on the bottom, but it's also due to their properties, the material that it's made out of. And so you get this kind of stickiness at a molecular level. So if I have rubber and I have concrete, there's always going to be the same coefficient of friction between the two, okay? And this is different than when I have, say, sandpaper and my hand. That also has a high friction, but part of that is due to a more mechanical shape of the sandpaper, right? It's rough on like a macroscopic level. That's usually a little different than what we're thinking about when we think of rubber touching each other, but the effect is still the same. We have kind of a stickiness between objects, so they don't just slide freely against each other, okay? And the stickiness between the two surfaces depends on what the two surfaces are made out of, okay? Metals of the same type tend to stick to each other really, really hard, okay? If they're just really like pure metals of the same type and I have two flat surfaces and I stick them together, they tend to stick to each other really, really hard. Something like, say, ice and rubber on the bottom of your shoes or on tires, well, those aren't very sticky, okay? Ice and rubber, they don't stick to each other very well at all, okay? So we have only a little bit of friction there. So in some extreme cases, we approximate a system as frictionless just so that we can focus more about the other things that are going on. And the classic choice in physics is we consider something that's sliding on ice, okay? That's always kind of a shorthand for consider this frictionless right now. But in real life, even with slick ice, there's friction between the ice and objects sliding along the ice, okay? And in general, our calculations are going to be off by some non-negligible amount if we approximate things as sliding without friction, okay? So in general, we're going to want to include friction when we draw free body diagrams like this, when we draw all the forces, okay? So there are two main types of friction that we want to consider. The first is kinetic friction. And we'll draw that as little f sub k, okay? Kinetic friction is friction that exists when things are moving, okay? So when the surface of this box here is sliding along the surface of the ramp, we have kinetic friction. So this has some v, okay? And kinetic friction is always opposite the motion, okay? So the force of kinetic friction is always going to point opposite to the motion of the object, okay? And it's going to be coming from this surface right here that's sliding along the surface of the ramp here. The other kind of friction that we're going to kind of commonly consider in this class is static friction. And we'll write that as F sub s. So static friction is a friction that exists when things are not moving. Okay? So for static friction, we take this velocity out of here. This thing's not moving anymore. And static friction is still coming from the surface of the box touching the ramp. But in this case, this friction force is going to oppose the net forces that are on the object. Okay? So remember, when we had this block with no friction, our net force in the x direction pointed this way. Okay? Well, let's write sum of the forces in the x direction. Okay? So our force of static friction now is always going to point opposite to the net forces, and it's always going to be perpendicular to the normal force. Okay? So static friction comes from two surfaces touching, and that interface between the two surfaces, I can draw a normal force coming out of it, just like I did here, okay, with this normal force. Static friction is always going to be perpendicular to that normal force where the two objects are touching, and it's always going to be opposite the direction of the sum of the forces in that direction. Okay? So in this case, I had, remember, gravity, I broke it down into components, and this piece of gravity in the x that was pointed along the ramp, it pointed down, so the sum of the rest of the forces pointed that way, so static friction points this other direction. Okay? And as it turns out, static friction is always larger than kinetic friction. So it actually takes more force to get something sliding than it does to keep it sliding once you get it moving. Okay? So while it's sitting still, I have to push it harder to get it to break loose and start to slide than I do to just keep it sliding after it's moving. So let's look first at kinetic friction. And this is occurring when one surface is sliding along another surface. So like we said, the friction is always opposite the direction of motion. So in this case, I have an acceleration that's going down the ramp. So my force of kinetic friction is pointing back up the ramp. The magnitude of kinetic friction is mu sub k times n, the normal force. Okay? The normal force, we know from before, is the force that the ground is pushing back up on the block with. And mu sub k is the coefficient of kinetic friction. And this is going to depend on what your two surfaces are made out of, okay? This is going to depend on the properties of the surfaces themselves, the materials that the surfaces are made out of. And so if you look at this equation, you note that Fk goes up as mu k goes up. Okay? So as my coefficient of friction gets bigger, the force of friction is bigger. Okay? So for the same object. So if I have ice and rubber, I would have one coefficient of friction. And if I had concrete and rubber, nice dry concrete and rubber, I would have a different coefficient of friction that's bigger, right? It's harder to slide rubber along dry concrete than it is to slide rubber along ice. So if I draw my coordinate like this, like I usually do with the block on a ramp problem, then you can see that my acceleration here is always going to be decreased by friction because it always opposes motion. Okay, so if I solved it in the same way that I solved the frictionless problem, now in the x direction, I would still have Fgx, but then in the minus x direction, I'm going to have this force of friction, right? and that's going to equal ma. And remember, when I didn't have friction, I just didn't have this term. So this term's always going to make A smaller. Okay, A is decreased by the force of kinetic friction. So what about static friction? What if we have a block problem with friction and the block is not moving? So then we could still use our same little clever coordinate system here, okay? And this still requires us to break down gravity into its components, FGY, FGX, and if we have some angle theta here, that still means that this angle is theta, okay? And we can break it down in components in a similar way. In the y direction, we still just have the normal force pointing up and the force of gravity, the y component of the force of gravity, pointing down. And we know that in the y direction, it's not moving, okay? So that didn't change from the last problem. In the x direction, we have the force of gravity in the x direction, the x component of the force of gravity, pointing in the positive x direction, and we have the force of static friction pointing in the negative x direction. But now we know that the object is not moving, so it must have an acceleration of 0, right? That was Newton's first law. If an object is not moving, it must have no net force on it, okay? So these must perfectly cancel. So then if we want to find the force of the static friction, then it's just equal to Fgx, which is equal to mg sine theta, okay? So if we had a problem where we had a box of some mass, or we had some object of some mass sitting on a hill, and we knew the coefficient of static friction, and we wanted to find out if the box was going to start sliding or not, okay, we could first solve for the force that static friction is going to be, and then we know that the maximum force that static friction can apply is mu sub s times n, and n is equal to Fgy based on this equation, okay? So that's equal to mu sub s times mg cosine theta, okay? And we can compare that to this. So if we have an object sitting on a hill, we can solve for the force of static friction that we know will be on the object based on the object's mass, and we can compare it to the maximum force that static friction could apply. If this one, the force that would be required to keep the box still, is bigger than this one, well then the box won't stay still. It will start to slide down the hill. If this one, the maximum possible force applied by static friction, is bigger than the force required to keep the box still, then the box will stay still, and the force applied by static friction will be this one, the one that's required. Static friction is kind of like all of us. It never does more than what is strictly required, okay? It only applies enough force to keep the object still. So I want to finish this lecture with one last generic example to highlight some concepts that'll be useful in your homework, okay? So look at this system that I've drawn. I have a ramp of some angle theta here, and I have two blocks, one that's on the ramp, and it's attached by a rope over a pulley to this block that's hanging from the ramp, okay? So we have the block on the ramp, 1, and the block hanging from the rope, 2. So generally when we deal with pulleys, we're going to assume that they're what's called an ideal pulley. And that means it's one without mass and without friction in the way that it works, okay? So this is obviously not physical. Pulleys do have friction when they spin, and they do have mass. But for our purposes, this is generally going to be an okay approximation to make, okay? Usually the mass that pulleys have is pretty small compared to the rest of the stuff that you're dealing with, and the amount of friction in a pulley, if it's a decent pulley, is usually pretty low. Okay, if it's a rusted old piece of garbage, friction's going to be pretty high. But a decent pulley is generally going to have friction that's pretty low, so it's generally fine for us to kind of consider them as ideal pulleys. And generally when we deal with a rope, we're going to assume kind of an ideal rope as well, where we consider it to be massless. Okay, so it doesn't sag like this. It has no mass. And it doesn't stretch at all. So as I pull on it or yank on it or whatever, there's no stretching of the rope. It just transfers that force directly into whatever it's attached to. Okay? So in a problem like this, whatever tension is on the rope is going to pull directly on this box. Okay? So I'm going to have T like this, pulling directly on this box from the rope. And the force along the rope, the tension, is just going to be redirected by an ideal pulley. So the tension's going along this way, right? And as it gets to the pulley, it just wraps around and goes this way. Okay? So this block is actually what's applying the tension to the rope. And all the pulley does is redirect the tension along the pulley. Okay? It just makes it curve. So tension will just keep pointing straight, and a pulley changes that. A pulley redirects the tension so that it points in a new direction. That's all it does. It doesn't change the magnitude of the tension. It's not changing anything else. It's just making the tension point in a new direction. So now let's take that knowledge and solve our simple problem here. We have block 1 and we have block 2. On block 1, we have just the force of gravity pulling down. Let's call this angle theta. And let's use our clever coordinate system. We'll point X up the ramp this time. And let's say that block 2 is heavier than block 1. Okay, so this system's going to move this way. So then we have the normal force pointing out from the ground, and we have tension running along the rope, T. And on block 2, we have tension pulling back up, and we have Fg of block 2 pointing down. Okay? In our clever coordinate system, we can break the components of gravity down like this. Not 2. Fgx. Okay? Now, the thing with our coordinate system is these two blocks are connected by this rope, and what a pulley does is convert us from one coordinate system to another because it just changes the direction of tension. And it's the only thing connecting these two blocks is these two blocks. So I'm perfectly free to just choose my own new coordinate system for block 2. Okay, and I'm just going to choose y hat is up for block 2. So then when we look at block 1, we would see that in the y direction, we have the normal force pointing up, and we have the y component of gravity pointing down, okay? And that's mg cos theta, okay? And that equals 0. Because the block doesn't fly off the ramp or fall through it. In the x direction, we have tension pointing in the positive x direction, and we have minus the x component of block 1's mass. Let me put a little 1 on this m. Block 1's mass pointing down. Okay, so the force of gravity on block 1 pointing down, m1g sine theta, and that's equal to m1 times a, and a is going to be in the positive x direction. Okay, because we said block 2 was heavier than block 1. So now, let's look at block 2. For block 2, we only have one direction. We just have the y direction. That's all we care about. And in that, we have tension is pointing up, and we have the force of gravity pointing down, right? The block's weight pointing down, and that's equal to the mass of block 2 times the acceleration. But we know that's going to be down, okay? In the system we've defined, that's going to be down, so I'm going to say minus A. Now, with a system like this, if the rope doesn't stretch, the first thing I should recognize is that if I move block 2 at all, block 1 has to move in the corresponding way, right? So they have to move together. So the acceleration of one block is going to have to be the same as the acceleration of the other block, okay? So the acceleration is the same on both. And with this problem, I should recognize that tension is going to follow Newton's third law, okay? This tension is an interaction between block 1 and block 2. Block 2 pulls on block 1, and block 1 pulls on block 2. So this tension is an interaction, and it must have just one magnitude. So the tension on block 2 must be exactly the same as the tension on block 1. So if I solve for tension of block on this equation with block 1, then I would get that it's equal to m1a plus m1g sine theta. Okay? And then I can set that equal to what I would get if I solved for tension in this equation, okay? If I solve for tension in this equation, I would have T equals m2 g minus a. And so I can set that equal over here, m2 times g minus a. And then I can use this equation and solve for a if that's what I'm interested in. Okay, so let's say that I'm interested in a. So I want to bring all the a's to one side. So I'd have m1a plus m2a equals m2g minus m1g sine theta. And so then A equals G times M2 minus M1 sine theta over M1 plus M2. The units on this are meters per second squared, and then that's all times this fraction that has meters on top. Sorry, not meters. That has mass on top and mass on the bottom. They cancel. I get meters per second squared, just like I should for an acceleration. The sanity so remember that theta is going to have to be less than 90 degrees. So sine theta is always less than 1. Okay? So A is always going to be less than G. Because we said M2 was bigger than M1. And it's minus up here. And it's plus down here. So A is always going to be less than G. And if we think about it, that makes sense, right? I shouldn't have A equal to free fall for either of the blocks because they're both pulling each other against gravity. So the interaction of the blocks means that A is always going to be less than gravity because they're not in free fall. They're pulling on each other, okay? So A is less than G, and that makes sense, okay? But then let's also I want to look at a special case. So what if theta was 90 degrees? Okay, let's think about that for a second. So I have a pulley, and I have block 2 sitting over here, and then I go over the pulley, and then block 1 is sitting on a ramp that has an angle above the horizontal of 90 degrees. What does that mean? That means block 1 is just hanging here, right? So then A just becomes little g, and then it's m2 minus m1 over m2 plus m1. And so again, I'm always going to be less than g because we said m2 was bigger than m1. Okay? And so the acceleration is always going to go in this direction, or for block 1, in this direction, right? But you can see that if I made m2 smaller than m1, I would get a sign flip in this top part, right? So if m2 was less than m1 and sine theta was 90, I would have m2 minus m1, and that would be a negative number if m1 was bigger than m2. And in that case, I'd get a negative sign out in my answer, and my accelerations would get flipped. And that makes sense too, right? That's what we would expect. I solved it for m2 greater than m1, but if I flipped it and made m1 greater than m2, it would slide the other way, okay? So that makes sense as well. So this is our magnitude for the acceleration in this problem. The direction is going to depend on the block, and we built that into the problem, right? We built it in by saying A was positive in this case because it's positive in this coordinate system, and it was negative in this case because it was negative in this coordinate system, okay? So this is a magnitude of A, and the direction of A is going to depend on which block we're talking about. And again, this is not an equation that you can use without proof in the future, okay? You can't, if you get a problem that looks just like this, a block over a pulley and another block, you cannot use this equation without deriving it. So you would have to solve the problem like I just did to get this same answer. So this concludes our lecture for today. Your homework will give you a chance to practice solving force problems and to practice applying friction to force problems.